So this is where we left off in terms of Chapter 5, and we're going to be moving on in this section. Racemic mixtures are essentially equal amounts of two enantiomers. So an example here, example here is S plus butane 2-ol and R minus butane 2-ol. Because there are equal amounts of both the plus and minus versions, you can have the notation being DL or plus minus. There's also no optical activity because right now you're going to have plus 13.5 and minus 13.5, and that mixture is going to lead to 0. The mixture also may have different boiling points as well as different melting points from the enantiomers. If an optically inactive reagent combines to form a chiral molecule, you usually generate a racemic mixture. So here's an optically inactive molecule. It's a ketone, where you can have hydrogenation occurring where the addition of the H is coming on the top or the bottom, generating the R form and the S form. And here you're going to have equal mixtures being formed to generate the racemic product. Optical purity. Optical purity is sometimes called enantiomeric excess, and you can calculate optical purity by taking the observed rotation and dividing it by the rotation of the pure enantiomer times 100. And this will tell you which enantiomer is present in greater amounts. So this asks to calculate the percent composition. The specific rotation of S2-iodobutane is plus 15.9. It's asking to determine the percent composition of a mixture that's R and S, especially if the specific rotation of the mixture is minus 3.18. So this is telling you, because it's a minus sign, that it's going to be the one that's going to be in excess is going to be lever rotatory. So if you know what the S is, which is plus 15.9, that means the R is going to be minus 15.9. In order to determine the optical rotation, you're going to take actually the minus signals. So there should be a minus and a minus in front of there. And when you divide those, it's going to be positive. So minus 3.18 divided by minus 15.9 times 100 is going to yield 20%. Now, in order to calculate what the percent composition is, you know that L, right? So we know that L minus D, because we know that it's lever rotatory, is going to be equal to 20%. Oops, sorry. Please bear with me. Okay, 20%. And then we also know that L plus D, is going to be equal to 100%. So if we know that, then from this we can calculate that 2L, right, is going to be equal to 120%, right? Because the D's are going to cancel out. From that, you can calculate a single L and then what a single D is, and that's how you can determine the percent composition. Chirality of conformers. If equilibrium exists between two chiral conformers, the molecule is not chiral. You can judge chirality by looking at the most symmetrical conformer, and cyclohexane can be considered to be planar on average. So let's look at an example. There are two chair conformations of cis-1,2-dibromocyclohexane shown here and here. The two chairs are non-superimposable, but the interconversion between these two is fast, and the molecules are in equilibrium. So in this case, any sample would be racemic and result in optical inactivity, and this also can be determined, as I had mentioned before, by looking at its plane of symmetry as shown here. But you can have what are called non-mobile conformers, in which you start off, for example, with this molecule. This does rotate, but the conformations over here of the bromine and iodine are in distinct places. This is the staggered conformation. Now, if we try to twist them so that they're planar, the problem is the bromines and the iodines will hit each other and will become crowded through the steric hindrance. So then twisting it so that it becomes the other staggered conformation is not possible. And so these two conformations are chiral. They are non-superimposable mirror images. Allenes. So some allenes are chiral even though they don't have a chiral carbon. Central carbon is sp hybridized, and in order to be chiral, the groups at the end of the carbons must have different groups. So let's look at an example. Here's penta-2,3-diene, shown here. These are two enantiomers of penta-2,3-diene, and if you build your models, which I suggest that you do, if you take this and also build a mirror image, these are not superimposable. As a result, because they are non-superimposable, these two molecules are chiral. Now, Fischer projections. So Fischer projections are a different way of actually drawing out structures. It's a flat representation of a 3D molecule. The chiral carbon is usually at the intersection of horizontal and vertical lines. Horizontal lines are forward out of the plane, and then vertical lines are behind the plane. So let me show you as an example. Here's the convention that we've been using, and so when you're drawing out this as these this wedged bond coming out of the plane, and this hashed bond going into the plane. And so if you view it from this angle, so your eye is drawn here, you're going to see that your H and the OH are going to be to the left and to the right, and your CH2OH is going to be on top, and CH3 is going to be on bottom. So when you draw it out, you're going to show it as hash going to the back, these coming out to the front, and so this is just looking at it in this view. Now if you take this and then draw a Fischer projection, which is a cross, you're going to then put H and OH, CH2OH, and CH3. And this is R propane 1,2-diol. You know that it's R propane 1,2-diol because the priorities are going to be, this is going to be 1, this is going to be 2, this is going to be 3, and this is going to be 4, and so you're going to go 1, 2, 3. That's going in the right hand or the clockwise direction, so you're assigning it R. This is more on Fischer projections. Again, this is now using kind of models, three-dimensional models, which you can do as well. And you're putting 4 different things to it, so that's chiral. You're viewing it from this angle. Again, 1 is going to be on your left, 4 is going to be on your right, 2 is going to be on your top, and 3 is going to be on the bottom. And so then when you make it on the cross for Fischer projections, that's what you get. Here's S-lactic acid. Again, left, right, top, bottom, left, right, top, bottom. Here's your Fischer projection in there. And determining whether it's R or S, again, we're going to decide by prioritizing 1, 2, 3. This is going in the clockwise direction, but the H is coming at us. As a result, you're going to reverse. Instead of it being an R, it's an S. And so that's what this is. Fischer rules. Carbon chain is on the vertical line. Highest oxidized carbon is often put at the top. rotation of 180 in the plane does not change the molecule, so you can rotate those Fisher projections, but rotation of 90 degrees is not allowed. So let's look at this example of 180 rotation being allowed. So here's your Fisher projection. Again, the convention is to put the carboxylic acid to the top. When you draw it out and you're rotating it, this is just drawing it out from the Fisher projection, you're rotating it 180 degrees where the carboxylic acid is on the bottom. And so this molecule and this molecule are the same. How do we know it's the same? We can then determine its rotation, whether it's R or S. Again, you're going to do 1, 2, 3, 1, 2, 3. This is going in the counterclockwise direction, but because the H is coming out, remember this is coming out, you're going to assign it the opposite rules, so it's going to be R. Let's look at it here. Here the assignment is 1, 2, 3. Again, it's going in the counterclockwise direction, but again, the H is coming out of the board, which then leads you to do the opposite configuration. Again, this is going to be R. If you do a 90-degree rotation, right, again, the carboxylic acid is up on the convention of the Fisher projection. This is now taking it from the Fisher projections to just the regular structures that we've seen. If we rotate it, now this carboxylic acid's to your right. Now this is an incorrect orientation, and this is actually an enantiomer of this. To confirm that, we can assign priorities. 1, 2, 3. This is going in the counterclockwise direction, but the H is coming out at us, so this will be R. And then if we look at this, the priority is going to be 1, 2, 3. This is also going in the counter clockwise direction, but this is going to the back of the board. Remember, these two are always coming out, and these two are going to the back. As a result, it's S. So these are not the same molecule. Glyceraldehyde, the arrow group from group 1 to group 2 to group 3 appears counterclockwise in the Fisher projection. If the molecule is turned over so that the hydrogen is in the back, the arrow is clockwise, so this is the R enantiomer of glyceraldehyde. Again, this is showing the priorities. This is going to be 1, 2, 3. Again, this is going counterclockwise, but since this is in the front, this is coming out, you're going to do the opposite. So that's why it's an R. Hydrogen is in the front, as I had shown you before, and then this is showing that you can then convert this into a Fisher projection, from a Fisher projection to the structures that we've been seeing, but I've shown you how you can actually take a Fisher projection and just count or determine R or S. It'll require some practice, but you should do this so that you know this in your sleep. So when naming RS from Fisher projections with hydrogen bond on a horizontal bond, like I've always been doing, just apply the normal rules backwards. Fisher mirror images. Fisher projections are easy to draw and make it easier to find enantiomers in internal mirror planes when the molecule has 2 or more chiral centers. So lowest priority, usually H, comes forward, so the assignment rules are oftentimes backwards, right? Because these bonds over here where the lowest priority of the H's are on the ones that are coming at us. Clockwise, 1, 2, 3 is S, counterclockwise, 1, 2, 3 is R, so we're doing the backwards rule. So let's do the determination of the stereocenters here. They're saying it's S, but let's confirm it. So this is going to be priority 1, this is 2, this is 3, this is going in the clockwise direction. We're going to, because this is coming out at us, we're going to reverse the Fisher, the nomenclature of RS, so this is going to be S. Let's do this one. 1, 2, 3. This is going in clockwise direction. Again, since this is coming out S, this is going to be an S. Diastereomers. Cis-trans isomerisms on double bonds are not necessarily enantiomers or mirror images of that are non-superimposable. Rather, they are not mirror images and they're not superimposable. So these stereoisomers here, cis and trans butene, are not mirror images. So because they're not mirror images, they're not enantiomers, but yet they are diastereomers, or there are stereoisomers because they are not superimposable. This relationship, where they're not mirror images and they're not superimposable, that they are diastereomers. So let's look at cis-trans isomers on rings. So here's enantiomers of trans 1,2-dimethylcyclopentane. There is no plane of symmetry, right, in this. So these are enantiomers that are chiral. However, the relationship of these molecules with the cis version, yes, this is achiral, but these two relationship are diastereomers. So diastereomers, they're oftentimes molecules with two or more chiral compounds, stereoisomers that are not mirror images. So let's look at this. There's the 2s3r form and the 2r3s form. This is a mirror image of one another. These are enantiomers. You can then put them on the different sides so that they're not on the same side, the bromine and the chlorine. And if you do a mirror image of those are enantiomers. However, the relationship between these sets of molecules with these sets of molecules are that they are diastereomers, because they are not necessarily mirror images, but they are non-superimposable. So when compounds have two or more chiral centers, they have enantiomers, diastereomers, or mesoisomers. Enantiomers have opposite configurations at each corresponding chiral carbon. Diastereomers have some matching and some opposite configurations. And then meso compounds have an internal mirror plane. Maximum number of isomers is 2 to the n, where n is the number of chiral compounds. So let's look at kind of the categories of the structures that we've been talking about. So all isomers, under all isomers you can have what are constitutional isomers or structural isomers, where the connectivities are different. And then there are stereoisomers, where you have the connectivity has some chirality to it. You have enantiomers, which are mirror images but non-superimposable, and then you have diastereomers, which are non-mirror images and non-superimposable. Under diastereomers, you can have cis-trans isomers or geometric isomers, or you can have other diastereomers where you have two or more chirality centers. Meso compounds. So meso compounds have a plane of symmetry, and we've discussed this. Here's cis 1,2-dichlorocyclopentane. Here's that plane of symmetry. This is dibromocyclohexane cis. This also has a plane of symmetry. But also within structures that are non-cyclic, you can have a plane of symmetry here. This would be meso 2,3-dibromobutane, meso-tartaric acid. If one image was rotated 180 degrees, then it could be superimposed on the other image if it's meso. So if we rotated these molecules 180 degrees, you should be able to, some of them, superimpose them. And then meso compounds are achiral even though they have chiral centers. Really important. So number of stereoisomers, we had just, in 2 slides ago, talked about the 2 to the n rule to determine the number of stereoisomers. 2 to the n rule only applies to compounds that don't have a plane of symmetry. So here are molecules. Again, we've seen this before in the sense these are mirror planes. This is enantiomer. And then this and this, because they have an internal mirror plane, these are meso compounds. But the relationship between this and this molecule, this and this molecule, that's a diastereomer, as well as this to here and this to here and this to here. So in this case, because of the plane of symmetry, you only have 3 stereoisomers, the plus minus diastereomer shown here, and the meso shown here. So the 2 to the n rule doesn't apply here. Properties of diastereomers. Diastereomers have different physical properties, so they can be easily separated. Enantiomers differ only in reaction with other chiral molecules and the direction in which the polarized light is rotated. Enantiomers are difficult to separate, and so what you can do is you convert enantiomers into diastereomers, and then you should be able to separate them because they have different physical properties. Louis Pasteur in 1848 noticed that the salt of a racemic plus minus tartaric acid crystallizes into mirror image crystals. And so using a microscope and a pair of tweezers, he separated the enantiomeric crystals. And so he was able to resolve the racemic mixture by just separating it out. But another way to separate out enantiomers is to take an enantiomeric mixture and react it so that you can form diastereomers. When you form diastereomers, they're not going to be mirror images, and because diastereomers have their different properties, you can then separate them. So what he could have done is take tartaric acid, or here you can take an R form of tartaric acid, the plus form, and take a racemic mixture, and then form the 2 diastereomers. Then you can separate them, and then hydrogenate so that you can separate out back into the RR tartaric acid and the alcohols that we're starting off with, the butanols, so that once you separate these out, then you can isolate these as separate entities. Nowadays, you can actually utilize what are called columns that are chiral. So columns that are packed with chiral material, they have a chiral material that you can react a molecule with. So if you have a racemic mixture that can react with that chiral column, one enantiomer will bind more tightly, another will less tightly, and so now you can separate out the 2 enantiomers. And so this concludes chapter 5. So again, please use your models. Again, please really start to understand how to determine RS configuration, and learn them so you're able to do this without really thinking without thinking too much, so that it becomes automatic.